So in this video, we're going to talk about power series and the radius of convergence. So in a previous video, when we were doing Taylor polynomials, we approximated e to the x with the following third degree Taylor polynomial. 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial. Well, if we would continue this pattern, it would continue until x to the n over n factorial. That would be the nth term. So I can get a precise value of e to the x with an infinite sum of x to the n over n factorial. And this sum would start at n equals 0 and go to infinity. So that infinite sum would represent the exact value of e to the x. And of course this is centered around x being 0. That Taylor series that we wrote was centered around x being 0. So here's another random infinite series, just to kind of show you the form of this infinite sum that we're going to write. It's going to start at n equals 0. It's going to go to infinity. And we have a to the n, x to the n. And this is called a power series. For this example, it's a power series centered around x being 0. Just like in our previous example with e to the x. Well, we could also have a power series centered around a number that's not 0. So how would that look? Well, it would look like this infinite sum. Now instead of just x, we have x minus c to the power of n. This is a power series centered around c. So we talked about it with our Taylor series polynomials, that the point of these are to estimate values of our function in and around where we're centered at. Well, only a certain amount of values of x in and around the center are going to be giving us good values. So that's where this radius and interval of convergence is. There's going to be a specific interval in and around the center that will yield results that converge, results that are good to us. So let's try a value. So in this example that we just did, that's centered at c, let's plug in our center value c, and let's see what happens. So in for x, I plugged in c, and I'm going to write a few terms here and see what this sum converges to, if it does converge. So my first term would be a sub 0 of 0 to the power of 0. Then I would have plus a sub 1 times 0 to the power of 1 plus a sub 2 times 0 to the power of 2. And that would continue on infinitely. And what are these values? Well, a sub 0 times 0 to the power of 0. 0 to the power of 0 is 1. So that would just be a sub 0. And the rest would be 0. So this infinite sum would equal a to the 1. Or, sorry, a to the 0. Whatever that a to the 0 term is. It converges to that value. So it converges at C. So every power series is going to converge at its center. So it's a matter of, are there any other values around it in which it'll converge? So on that note, your interval of convergence is going to be one of these three. It's either going to only converge at C and C only. It's going to have some interval x minus c less than r, or it's going to converge for all of x. And we'll get some examples of all three here in a second. But basically it's going to be one of these three. So here's a first example. Find the radius of convergence and the interval of convergence. It's centered at 0. We can tell because there's no x minus c in our power series. So if we're going to find the interval of convergence, I need to know some x values in which the sum will converge. So here I'm just going to show you again one more time that if you plug in the c value of the center, you're going to get convergence every single time. That's going to be a guarantee. So if I plug in 0 for x, the terms of my sum become 1 plus 0 plus 0 plus 0. So that sum is going to converge to 1. So it definitely does converge at the center. To find other values, we need to do the ratio test. So we got to think back to the ratio test and how we got that. Well, each term in my series is n factorial times x to the n. And how we did the ratio test was, it was the limit as n approaches infinity of the absolute value a sub n plus 1 over a sub n. And the result of this limit would indicate to us values of x in which it was either converging or diverging. So to do this, first I'm going to get n plus 1, so that's n plus 1 factorial times x to the power of n plus 1 all over n factorial times x to the n. And the nice thing about doing these is usually there's a lot of cancellation that occurs. There's usually a major simplification process. So if I simplify this, I end up with the limit as n approaches infinity of n plus 1 times x. And I'm going to put the x on the outside here. I'm basically going to factor out that x, because really the x has no implication in the limit, because the limit is n approaching infinity. Alright, so as n approaches infinity, this overall limit will approach infinity. And with the ratio test, our goal was to basically compare that solution to 1. So are there any x values in which the solution to this limit is less than 1? Well, it appears that the solution to this limit is always infinity, is always greater than 1. So there are no x values in which the infinite sum will converge. It's divergent for all x values except for that center when x was 0. So that's an example of the first possible result that I showed you a moment ago, that the series only converges at C, which in this case is 0. So the only value of x for which this power series converges is 0. which would mean that the radius of convergence would also be 0. The radius of convergence is kind of how far left and right of that center are you going to go to have an interval of convergence. Well, if the center is the only value of x in which there's convergence, the radius of convergence is 0. So there's another example for you. I'm not going to show that the center converges again. Instead, I'm just going to jump right to that ratio test. So the limit as n approaches infinity. On top, I'm going to write a sub n plus 1. On the bottom, I'm going to write a sub n. And I'm going to see what all cancels to simplify this limit and get a solution to this limit. So try to follow me as I work through this. Try to follow my thought process. It can be a little confusing how to get the n plus 1 numerator. Well, if I started with 2n plus 1, and in for n, I'm going to plug in n plus 1, then it's 2 times n plus 1 plus 1. And I kind of showed that work on the side there. So that's how I end up with 2n plus 3. Alright, so when the dust settles from this limit and we get everything to cancel that can cancel, the simplified limit becomes limit as n approaches infinity of x squared all over 2n plus 3 times 2n plus 2. So if you compute that with the limit as n approaches infinity, that limit is going to go to 0. So for all values of x, that limit is going to be equal to 0. So that's nice, because in our ratio test, we compared that result to 1. 0 is less than 1. And since 0 is going to be the result of our limit for all values of x, it appears with this power series that it's convergent for all values of x. So not just the center, but for all values of x. And since it's convergent for all values of x, we would say that our radius of convergence is infinity. Okay, another example for you. Again, we're going to find the interval of convergence and the radius of convergence. So setting up my limit to do my ratio test. Try to follow me with my work here. Once you kind of get practice with simplifying these fractions, you get better at them. They begin to go pretty quick. This takes a little bit of practice, but try to follow my work. So the simplified version of this limit, the limit as n approaches infinity, is going to be x plus 1 over 2. So that is the result of this limit, the absolute value of x plus 1 over 2. So again, the ratio test compares this result to 1. So if I write that as an inequality less than 1, this is basically telling me the x values in which there will be convergence. So basically I need to solve this inequality to get my interval. So first step would be multiplying by 2. So that kind of gives me an indication of where my center is. My center is at minus 1. And this also tells me what my radius of convergence is. My radius of convergence is going to be 2. And we'll see that a little better if I solve this absolute value inequality. That kind of goes back to Algebra 2 days. If I solve this absolute value inequality, I end up with negative 2 less than x plus 1 less than 2. My final inequality, negative 3 less than x less than 1. So the center of that interval is negative 1. And the radius, or how much we're going left and right of that center, is 2. So that is my interval of convergence. So we're almost done here. Last thing you have to do after you have your interval is check the endpoints. So I need to check negative 3, and I need to check 1. So I'm going to plug in x is negative 3 back into my original problem. When I plug in negative 3 into the original problem, that infinite sum will become 2n over 2n, which is 1. So for each term, I'm going to have a value of 1. So that infinite sum is going to be 1 plus 1 plus 1. That infinite sum diverges. So when x is negative 3, the power series diverges. So I'm not going to include negative 3 in my interval. Okay, let's do the other endpoint. The other endpoint was positive 1. So I'm going to plug in positive 1 back into my original infinite sum. When I plug in power or positive 1, the result that I get is the sum of n equals 0 to infinity of negative 1 to the power of n. So when I list those terms, I get negative 1, positive 1, negative 1, positive 1. If you recall, that is an alternating series, so that diverges. So both endpoints, negative 3 and 1, diverge. So I'm not going to include that in my interval. The interval of convergence for this problem is negative 3 to positive 1, not inclusive. And if you wanted to write that in interval notation, it would be negative 3 and 1 with the parentheses around the ends. Alright, I believe I got one more example for you. We're going to do the infinite sum, this time from n equals 1 to infinity. X to the n over n. So I'm going to quickly get this limit simplified for my ratio test. So when I simplify this limit, it becomes just x. As n approaches infinity, it's just x. So again, with ratio test, I'm concerned with comparing that result to the value of 1. So I'm going to compare absolute value of x to 1. If it's less than 1, then it converges. So this problem is centered at 0, and it has a radius of 1. And we see that if we expand this absolute value inequality. That inequality is negative 1 less than x less than 1. So from there we see where the center is. The center is at 0, and the radius is 1. So last thing I got to do is just test those endpoints. Let's test negative 1 into the original infinite sum, and also test x equals 1. So first value I'm going to test is x equals 1. That results in 1 over n. So if you were to list these terms to kind of see what's happening, you get 1 over 1 plus 1 over 2 plus 1 over 3. That is a diverging series. So when x equals 1, it diverges. So we're not going to include that in the interval of convergence. Now when I test x equals negative 1, the infinite sum that I get as a result is negative 1 to the power of n all over n. When I list some of these terms to see what's happening, I get negative 1 plus 1/2 minus 1/3 plus 1/4. So that is a sum that is converging. So it would appear that when x equals negative 1, I want to include that in my interval of convergence. So I'm going to write my final interval of convergence. It's going to go from negative 1 to 1. It's not going to include positive 1, but it's going to include negative 1.